Today we discuss the Fibonacci numbers. You can see by my two hearts that I love the Fibonacci numbers. They are some of the most beautiful numbers in mathematics. These numbers are denoted Fn and they're defined recursively. Well, just like we discussed a few recursively defined functions in the last video, we can give a recursive definition for Fibonacci numbers. Well, F1 is 1, F2 is 1, and then for n bigger than or equal to 3, Fn is Fn minus 1 plus Fn minus 2. This is the recursive definition for Fibonacci numbers. Well, let's just write out a few. Okay, 1 and 1. This is F1, F2, and then we add, we get 2. Then we add 3, we add 5, we add 8, we add 13, we add 21, okay, like this. So these are, I can do one more, we add, this is 34, and this continues. Okay, these are Fibonacci numbers here. In fact, we can label them. Sometimes you will see 1 here. You will see 0 listed first as an F0. Sometimes this is needed for some sort of identity, but I'm putting it in green just as a comment. These come up so much in math, so much in nature, and there is a TED Talk you absolutely must watch after you watch this lesson. It's very cool about the Fibonacci numbers. I will link to it. Okay, now, what do we want to do? Well, the beauty of these numbers is there are many relationships among the Fibonacci numbers. This is one of the things that makes them so cool. And how are you going to prove a relationship among the Fibonacci numbers? Well, you see, we have this defining recurrence. And so many of these relationships we can prove using induction or strong induction. And this is what we will practice some today. Here's our first example. This says, if you add the first n Fibonacci numbers, you get Fn plus 2 minus 1. So let's prove this using induction. N equals 1. Well, the left-hand side just has one term. The left-hand side is F1, which is 1. And the right-hand side is F3 minus 1. We just erased. We had a few Fibonacci numbers calculated, but F3 was 2. So this is 2 minus 1, which is 1. And so our basis step is complete. Now for the inductive step, we assume K is a natural number with, well, if you add I equals 1 to k of fi, we get fk plus 2 minus 1. And then we will show, if we add I equals 1 to k plus 1, fi, we get f. This would be k plus 3 minus 1. This is our goal. So let's start with the left-hand side. And you see, because I will use my inductive hypothesis, I will write the first k and then write the k plus first term. Our inductive hypothesis is that the sum of the first k Fibonacci numbers is fk plus 2 minus 1. So I will use that right here. This is equal to fk plus 2 minus 1, and then I just recopy fk plus 1. Okay, this is where I use my inductive hypothesis. Now, finally, the last thing to do is we use the defining, well, it's not written on the board anymore, but what? Define the Fibonacci numbers, that if you add two consecutive Fibonacci numbers, you get the next one. And that's what I see here. I have fk plus 1, I have fk plus 2, and so the sum of those two is fk plus 3. And then I have this minus 1, and we are finished. This was what we wanted to show. This is the end of this proof. This last part, though, just a comment, going here to here, this was not an inductive hypothesis. The only inductive hypothesis was this underlined in green to be this right here. This last step was because we're working with Fibonacci numbers. And you notice also, this is not strong induction. This is just normal induction, where I used the statement for k, and only for k, to prove the statement for k plus 1 here, right? My first example was about the sum of the first n Fibonacci numbers. This one is about the sum of the squares of the first n Fibonacci numbers. And we will prove it's fn times fn plus 1. Again, by induction, again we have basis step and an inductive step. Our basis step involves verifying for n equals 1, just like in the first problem. The left-hand side is just one term. So this would be f1 squared. And f1 is 1. So we get 1 squared, which is 1. The right-hand side, this would be f1 times f2. Both of these are 1, and so we get 1 here as well. We have verified our basis step. Now for the inductive step. Assume we have a natural number k with, if you add the squares of the first k Fibonacci numbers, we get fk plus 1. And then we need to show, if we add the first k plus 1 squares of Fibonacci numbers, this should be fk plus 1 times fk plus 2. Now this begins very much like the last one, where we will write the sum of the first k plus 1 as the sum of the first k plus this. This will be fk plus 1 squared. And then we have our inductive hypothesis, which, oh, I forgot my squared. Okay, now it is correct. And now I can use my inductive hypothesis, which says that this is fk times fk plus 1. So this is fk plus 1, and then we have plus fk plus 1 squared. Well, you see what we're trying to show? We're not quite there yet. Well, of course, we shouldn't be there yet, because nowhere yet, except for in the basis step, have we used that these are Fibonacci numbers. So let's factor out what's common to both here, which is fk plus 1, and then we have fk plus 1. And this is when we can use that we're actually working with Fibonacci numbers. Fk plus 1 is fk plus 2. So this is fk plus 1 times fk plus 2, and this was exactly what we were wanting to show. And this is the end of this proof. My next example is a little more involved, but it's also very fun, I think. We will prove this, that fn minus 1 times fn plus 1 minus fn squared is minus 1 to the n for integers n bigger than or equal to 2. And I'm putting 2 there instead of natural numbers because here, when you have n equals 2, this is where we see a f1. But just as a comment, down here when I was talking about the Fibonacci numbers, I said sometimes people will have F0, and that is 0. If you take that, then you could prove this for natural numbers n. You would just have F0 here, and it would be 0. But we will prove it just as it's written. The basis step is n equals 2, and this is just a verification. This says, well, the left-hand side is F1, F3 minus F2 squared. And F1 times F3 is 2, and this is 1 times 2, minus 1 squared, this is 1. And the right-hand side, this is minus 1 squared, which is also 1. And so our basis step is complete. Now for the inductive step. Let's assume k greater than or equal to 2 is an integer with fk minus 1, fk plus 1, minus fk squared is minus 1 to the k. And we need to show, well, the statement for k plus 1. So let's write that. That would be fk. It would be fk plus 2 minus fk plus 1 squared is minus 1 to the k plus 1. Well, let's start with the left-hand side. This is fk plus 2 minus fk plus 1 squared. Now might be the time where you get stuck and you're not sure what to do, but we do know these are Fibonacci numbers. So we must use that if you take two consecutive Fibonacci numbers and add, you get the next one. That must be used somewhere. But also, we need to use this somewhere. So let me start. I will expand this, and I will expand one of these. We know fk plus 2 is fk plus 1 plus fk. This is fk plus 1 plus fk. This is what makes these Fibonacci numbers. And then I have this minus. I will write one of these, and the other one, fk plus 1 is fk plus fk minus 1. Why did I think to do this? Well, I want an fk squared, and I know I need an fk minus 1 multiplied by an fk plus 1. And then, really, if we multiply all this out, we will have 4 terms, but hopefully 2 of them add to 0. So let's see what we have here. So this and this adds to 0, and I'm left with fk minus fk plus 1, fk minus 1. Okay. Now this is when we realize things might work out the way we want them to. In fact, I can factor out a minus 1. Well, let me write this in the order to match the above. Fk minus 1, fk plus 1, and then minus fk squared. Okay? Well, by our inductive hypothesis, this is minus 1 to the k. So we have minus 1 to the k, which is minus 1 to the k plus 1. This is exactly what we were trying to prove. So you see, just like the first two, which were, in my opinion, much more straightforward, we still used induction. We still used what defines Fibonacci numbers. In fact, I used the defining recurrence twice, here and here, and that's perfectly fine. I used the inductive hypothesis just one time, right? That was here. In fact, I could label it. It was here. But you can imagine there are so many beautiful formulas that relate Fibonacci numbers, and we've seen only 3, but you have more you can work on in the exercises and more you could dream about, I suppose. Now, let's do one more example today, which is also super fun. Let's prove for natural numbers n that fn is less than or equal to phi to the n minus 1. Phi is what's called the golden ratio. It's this number right here. It's 1 plus the square root of 5 over 2. Now, before we get into the proof of this statement, I need to verify a claim that we will use, and that is that phi squared is 1 plus phi. So let's prove this, but it's relatively short. Well, let's consider x squared minus x minus 1 equals 0. This is a quadratic equal to 0. We know the solutions. This would be quadratic formula. If you remember this from math classes, it would be negative b plus or minus the square root b squared minus 4ac all over 2a. That would be for ax squared plus bx plus c, but I wrote this out with our particular coefficients. And if we just simplify this, this is 1 plus or minus the square root of 5 over 2. And you see, one of these is phi, this golden ratio, and in particular that says phi squared minus phi minus 1 is 0. It's exactly the same as this claim. So we have proven the claim. Now we will prove this upper bound on the Fibonacci numbers fn using strong induction. This is our first example where we will need this statement for both k and k minus 1 in order to prove it holds for k plus 1. So this means 2 cases to check in our basis step. This would be f1 and f2. These are both 1. f1 is 1. This is equal to phi to the 0. Any number raised to the 0 power is 1. And then I need to compare 1 and phi to the 1. That would be this with n equals 2. Well, if we look at this without using our calculator, we can see certainly that number is bigger than 3/2. So I could do this. In fact, phi is about 1.618, and then there are some more numbers. But in any case, we have our basis step. Now for the inductive step, we assume k is bigger than or equal to the highest thing we proved with 4. Well, this would be 1 less than or equal to n less than or equal to k. fn is less than or equal to phi to the n minus 1. And then we need to show fk plus 1 is less than or equal to phi to the k. Well, I will use first what it means to be a Fibonacci number, namely fk plus 1 is fk plus fk minus 1. And then, just like I said, I will use, well, it's here, the inductive hypothesis for both fk and for fk minus 1. So this would be less than or equal to, this would be phi to the k minus 1 plus phi to the k minus 2. This is by the inductive hypothesis. Now, let's factor out what's common to both terms. Both terms have a phi to the k minus 2. And here I would have a phi, and here I have a 1. If you do not believe this, just check. This is a phi to the 1. If I multiply these two, I get phi to the k minus 1. If I multiply this times 1, then I have this term. Well, you see, This is the claim, which you can just look up and see it in purple. We also proved this, that phi plus 1 is phi squared. And now we can add exponents, we get phi to the k. And this is exactly what we wanted. This is the end of this proof. It was a proof using strong induction that gives us this upper bound on the Fibonacci numbers. What we are looking at graphically in Desmos is in part something we just proved, and in part something you will prove in the exercises. So this, I've labeled it A here, but this is this golden ratio, 1 plus square root of 5 divided by 2. And then you notice the blue and the green, one is the graph of this phi raised to the x minus 1, and one is phi to the x minus 2. Now, if you look just at the integer values, we would get phi to the n minus 1, phi to the n minus 2. And we proved that the nth Fibonacci number is less than or equal to phi to the n minus 1. And what we see in this graph is that the Fibonacci numbers sit underneath this blue curve. Now, you will prove in the exercises that the nth Fibonacci number is greater than or equal to phi to the n minus 2. And you can see this in this graph because these red dots, these are the Fibonacci numbers, they sit above this green curve. And so it's interesting to see graphically, and this doesn't just hold for the first 7 or so. I could zoom out and go up, and we see this holding more. But what you can see graphically is sort of the combination of these two statements, that the Fibonacci numbers sit between phi to the n minus 1 and phi to the n minus 2. Now, there's one more thing I'd like to show you. What are we looking at? Well, I hope you say Pascal's triangle, of course, because we looked at this earlier in the semester and it's one of my favorite things. But another one of my favorite things is Fibonacci numbers. And guess what? Let's see the Fibonacci numbers now. So we still see Pascal's triangle, but now look what we see. 1, 1, 2, and then add these two. 3, add these two. 5, add these two. 8, etc. So these are the Fibonacci numbers. We start with 2 1s, and then you add 2 consecutive ones to get the next. But how they are related to Pascal's triangle really comes from these diagonals. If we add, sort of as I colored this to indicate, you get exactly the corresponding Fibonacci number. And this would continue in this sort of infinite Pascal's triangle. You would keep adding and you will get the Fibonacci numbers. Now, there is an identity here. You could write down the corresponding sum of binomial coefficients and the Fibonacci number, and you could prove, if you wanted to, that you get equality there. But what I wanted to do is just show you this because I think it is a really cool thing we could see visually with the color, but also it's a really neat idea that connects this new beautiful thing, Fibonacci numbers, with Pascal's triangle, which we studied earlier in the semester. So, thank you.